here is the situation. We have a 50-foot cable, and it weighs 100 pounds, the cable itself. And it's used to pull an elevator weighing 1,000 pounds up. How much work is required to pull both the cable and the elevator the entire 50 feet that it is hanging down? So here's our situation. We have, right, the top of where the elevator is going to get pulled to. And then we have, right, the cable. And then at the bottom, we have the elevator. The elevator weighs 1,000 pounds. So, and the cable is 50 feet long. And there's actually kind of two things to talk about here. The first thing I want to mention is that people like to set up their kind of frame of reference in different ways. I am a big fan personally of making kind of the bottom of my setup, with some exceptions, but almost always, I like to make the bottom my 0. So I often say, oh, this is x equals 0. And then since it's 50 feet long, this would be x equal to 50. Actually, I'm going to use y, because when I do, I usually using y. I'm going to do it in a different color too and use x instead. Other people like to say, this is x equals 0 up here, and this is x equals 50 down here. And the truth of the matter is it doesn't matter which way you do it as long as you do it right. Meaning as long as you set up your thing consistently, it'll work out correctly either way. I should also say, before we even get going on this, there's two different things to calculate here. There's the work for the elevator, and there's the work for the cable. The work for the elevator is super easy. The work for the elevator is just going to be, well, it's a force or weight of 1,000 pounds, and it's going to travel a distance of 50 feet. So the work for the elevator is going to be 1,000 pounds times 50 feet, which is 50,000 foot-pounds, which I really enjoy saying, I'm not going to lie. Foot-pounds, foot-pounds, foot-pounds. So that's the work for the elevator, which is the nice, easy part of this problem. The work for the cable, on the other hand, is going to require more work. Yeah, I know. There's a lot of lame work jokes that get made when you're talking about work. Oh well, it's true. So here's the deal. And we're gonna look at a small portion of this. And the thing I was noticing when I was thinking about this problem before classes, there's really kind of two ways to think about what we're doing here. You can either, and so I'm going to talk about it both ways. You can either think of it as, okay, this small segment of the cable weighs some amount, and that small segment is going to move this distance. That's how I usually think of it. So depending on how we're doing this, right? If we're saying that so I'm gonna draw two different ways. If we're going from y equals 0 to y equals 50, then this is at a height of y, and it's going to move a distance of 50 minus y. Other people prefer to just say, oh, well, this is x away from where it's moving to. Also fine. How much does the elevator cable weigh? The elevator cable weighs 100 pounds, and it is 50 feet long, which is definitely important. We're going to do that in a minute. Okay, so I like to think about this part here, so the work for this little part, well, and again, so this is where people kind of vary. I think of it this way. I think, okay, this little segment, so the work for this segment here, which I'm going to say is dy long. So the work for that little section there is going to be, well, it's going to be force times distance. Force is just a fancy word for weight. How much does that little segment weigh? Well, what's the weight density of the cable? The cable is 50 feet long. It weighs 100 pounds. So the cable weighs 100 pounds per 50 feet. So the cable weighs 2 pounds per foot. So each foot weighs 2 pounds. How long is this? Oh, that section is dy feet long. So maybe it's half a foot. If it was half a foot, it would weigh 1 pound. Or maybe it's a quarter of a foot and it weighs half a pound. Or maybe it's a really small part of a foot and it weighs twice that many pounds. So this segment here, the weight of that segment is 2 pounds times, 2 pounds per foot times dy feet. Or I would just write 2, right? But really, or 2 dy, I should say, right? The feet cancel and you get 2 pounds times dy. So the weight of this small is 2 pounds times dy, where dy is how long it is. Okay? The distance, if you're doing it the red way that I've done it here, the distance this segment has to travel is 50 minus y. So if I was going to set it up this way, I would say, okay, the total work for the cable is going to be the integral from, well, these little strips go as low as y equals 0 and as high as y equals 50. So the integral from 0 to 50 of my force, which is 2 dy, times my distance, which is 50 minus y. Sorry. And I'm going to put the dy at the end. That is one way we could set this up, which would be totally correct. I feel like there's something I'm not quite saying right, and I want to make sure I am saying it right. No, that looks fine, I guess. My brain is forgetting something. No, I guess that's fine. Sure, okay, yeah. What I'm trying to say is, right, this 2 dy part, this 2 pounds dy, this is like an infinitesimal force, right? It's a very small weight. We do not have to keep the units. We're gonna get the units at the end, but since we know we're calculating work, we know our units should either be, if it's in the US system, force times distance, which is pounds times feet in this particular example. Yeah, so I'm about to, if the elevator cable weighs 100 minus 2 times 50 minus y. So I'm just talking about this small segment here. Yeah, so that's kind of the other way. So yeah, you can also kind of think of it this different way. Although I'm less good at thinking of it that way, Morgan. So the other way, we could obviously do the same sort of thing over here. I'm going to erase this elevator part because we'll come back to that. Right? The elevator work was easy. But you could also do, so I'm going to write it this way just for a second, and then we can talk about what you're saying. So here, we could think of the work as being, so again, one way to think of it is as it's how much this part weighs times how much it travels. And this part weighs 2 dx, and it travels a distance of x. And x, the distance it's traveling, can be as small as 0 or as large as 50. That is one way you can think about it. But another way to think about this is, and so I'm going to have a little bit of trouble saying this, I'm not going to lie, but I'm going to try and get it right. So instead of thinking of having a small weight that's traveling a certain distance, you can instead say this length of cable is going to travel a small distance. So basically, all of the cable from here to here is going to travel up a little bit. So now I'm actually kind of thinking of it differently, that the distance traveled is the dx, right? I'm calling this dx. And the force, or the weight, is, well, the force is how much cable you have, in this case x, times the density of the cable, which was 2 pounds per foot. So it's still going to work out the same this way, but I will point out, right, it is a little bit different way of thinking about it. Now, I want to kind of go back to this side and see if what you're saying makes sense, Morgan, because I'm not exactly sure. I'm going to erase the problem because I think we all know what the problem is at this point. So can I think of this one in that same way? So if I think of the red one here, so what I do want to point out actually before I get going any further is whether you do it this way, whether it's 0 to 50, the integral 2 times 50 minus y, or the integral from 0 to 50 of 2x dx or 2y dy, you're going to get the same result either way. So no matter if you're thinking of the top being 0 and the bottom being 50, or the bottom being 0 and the top being 50, it's going to work out okay. But let me answer your question. So if I was trying to think of it in this other way, where I'm thinking, okay, the distance it's going to travel is the little dy amount, and the force is the weight of how much cable that we have to move. So we're moving 50 minus y's length of cable, but it weighs 2 pounds per foot. And is that the same as what you're saying? I don't think it's quite the same. Yeah, I'm not sure. You're saying 100 minus 2. I think it would have to be, no, I don't know. Like the total minus what was already pulled up. So you're thinking about the weight. Yeah. I don't know. That's a good question. I don't think so, but I'm not able right this moment to say why. Yeah, let me think about this for 1 sec. So I guess I'm kind of thinking like if it was, right, so yeah, we're thinking about like if you had all the cable out and it's moving a little bit, then the amount of work that the amount of force it has is essentially all the cable, which is x long times the weight density. So I don't think we can do it that way for this one, Morgan. I don't believe it'll come out right. Either way, here's what's going to happen. So if you do it this way, you're going to integrate. So there is, I don't like doing it this way as much because I feel like I like to make the bottom smaller and the top higher. Oh, really? It does? Okay, then I guess it works out. Okay, so in this case, you're going to get the integral of 2x dx from 0 to 50, which is going to be x squared evaluated from 0 to 50, which is going to be 2,500 minus 0. So then the total work would be the 2,500 plus the 50,000, which would be 52,500. Right, 2,500. For this one, it's going to be the same, but it's a little bit more work. So this integral is a little bit less nice. It's going to be, so I'm integrating from 0 to 50, 100 minus 2y, which is going to give me 100y minus y squared from 0 to 50. If you plug in the 50, you get 5,000. Plug in the 50 here, you get minus 2,500. Oh yeah, it's the same. So again, the total work is still 50,000 plus the 2,500. Yeah, that's, I'm getting 2,500, Morgan. I guess I'm not sure what your question is. Yeah, so either way. But again, I don't know if doing it the way that you were writing before works out or not. You seem to say it does, but I feel like doing it that way just feels a little more complicated. I'm trying, in my opinion, to make the process as kind of simple as possible. So I'm usually going to think of it as, oh, this little segment weighs a certain amount, and I'm going to think about how much work it takes to move that segment that weighs a certain amount, how far away it is from where it's going to. Okay. Should we do another one like this, or should we move on to some of the fluid ones? Okay, another one of these. Let me grab one here. Where did I put them all? Okay. I mean, I will say, once you've done one of these, they kind of all are very similar. So the units here are foot-pounds because it's the US system. Right, so the answer at the end is 52,500 foot-pounds, which sounds kind of dumb, but in the US system, it's just force times distance, which is force pounds times distance. In the US system, it would definitely be joules, or Newton meters, which are joules. in the metric system. I might have said US accidentally. Sure, yeah. Well, I don't want, so converting this to joules, I would never give a student a problem in the US system and ask them to convert it to the metric system. That seems cruel. We can definitely do a problem in the metric system and talk about the answers. But like if you're going to convert this to, so I mean, okay, I will briefly mention how you would do this. It is not a good idea. So basically, you're trying to convert foot-pounds to Newton meters. So how do you convert pounds to newtons? I mean, we could, right? Pounds are, well, I know 1 pound is 2.2046 kilograms. So 1 pound should be a Newton. A Newton is a kilogram times a meter per second squared. So that's going to be like, you shouldn't do it this way, right? Like this is not the right idea. But we can definitely talk about if you were given a problem in the metric system, how the answer would look. So basically, you'd have to convert each of the different things to their corresponding metric system values, which is just blah. So let's look at this next one. A ship's anchor is 4,000 kilograms. And where'd you go? Sorry. It's hanging from a 1,000 foot, what's the word I'm looking for? Chain? Cable? Sure. That weighs itself 3,000 pounds. Sorry, 3,000. Sorry. So, I'm so used to doing it in the US system. A 1,000 meter cable that weighs 3,000 kilograms. These numbers might not be very accurate. That's all right. Doesn't really matter. How much work to lift the anchor off from its fully extended? How much work to lift the anchor 1,000 meters? So the anchor, so here's the picture. So the boat's living right here. We're ignoring like the resistance due to water. And the anchor is in the ocean. That's the situation. So we're asking, how much work is it going to take to lift this up 1,000 meters? Okay, so again, I'm thinking of this the same sort of way. And I'm going to call this small segment dy. And I want to know how much that small segment weighs, or what's the force that small segment's exerting. So I'm going to say, okay, the force here is dy, how long that piece is, times the weight density of that piece. And the weight density of the cable is 3,000 kilograms per 1,000 meters, or 3 kilograms per meter. So the weight of that small segment is 3 kilograms per meter times dy meters. Or just 3 is what I would write in my interval. Okay, and then really we have to decide how we want to set it up. Do we want to call the bottom y equals 0 and the top y equals 1,000? That's what I usually want to do, just because it feels natural to me. Now, I will again state, doing it this way does make the integral a tiny bit more, it involves more effort to calculate the integral if we do it this way. Just a little bit though. So let's see what we get. So I'm going to say the work for this little piece is the force, which is 3 kilograms. I don't really want to write the units. It's 3 dy times the distance it's going to travel, which, so again, if this is the bottom, I'm thinking of this as being at a height of y, and it has to travel a distance of 1,000 minus y. So then we're going to integrate that. We're going to integrate from as low as the bottom 0, right? Because that's where the bottom part is, to as high as 1,000. So that's going to be the integral from 0 to 1,000 of 3 times 1,000 minus y dy. And that's going to be, so then we're going to integrate this. We're going to get 1,000y minus y squared over 2 from 0 to 1,000. And this happens a lot. And what's kind of interesting here is you'll notice that when you plug in 1,000, you get 1,000 times 1,000, which is 1,000 squared, minus when you plug in 1,000 here, you get 1,000 squared over 2. So you get 1,000 squared minus half of 1,000 squared, which is going to give you half of 1,000 squared. So this part is going to give you 3 times half of 1,000 squared. Half 1,000 squared is a million. Half of a million is 500,000. So you get 3 times 500,000, which is 1.5 million. Now, I forgot something. That's okay. It happens. It's easy to fix. I forgot to multiply by 9.8 meters per second squared. Right? All I found currently, so my force actually isn't a force. Yeah, right? My force here is just a mass, which is not a force, right? Force is mass times acceleration. So we actually need to also multiply here by 9.8. So all of these should be, right, this should be multiplied by 9.8. So I should have a 9.8 times all of this stuff. I know I read it from, but, so, yeah. Right, that's the one thing that is always like why I don't usually prefer to do it in the metric system, because you're always having to multiply with this 9.8, which is just not nice. Whereas in the US system, they always give you just the weight instead of the mass, so it's kind of already baked in. So 9.8 times 1.5 million is a lot. It's 14 million, yeah, 14,700,000. This is 14,700,000 joules, right? Newton's meters, or Newton meters. That's not the whole story though. Right? There's also the work to be done from lifting just the anchor. This was the work for the cable. So the work for the anchor, that's the easy part. The work for the anchor, well, the anchor is just all one mass right there of 4,000 kilograms. So the work for the anchor is going to be the 4,000 kilograms times the 1,000 meters that mass travels times the 9.8 meters per second squared. So in this case, that's going to be 4,000, or 4,000 times 1,000 is 4 million, times 9.8 is over like almost 40 million, 39.2 million. So the total would be the 32 million plus the 14 million. It would be a total of 46,900,000 joules. They're probably numbers that are unrealistic, but again, it's okay. So again, really make sure you're thinking of this in a way that makes sense for you. My thought process again is really to think of this as some small weight, it's traveling some distance, but other people like to think of it as, okay, you've got this amount, like, so once you pull the anchor up to here, that's the thing I didn't say before. So, right, so like you've gone along the process and the anchor has gotten up to like this spot here. So it still has, you know, this much left to travel, which is 1,000 minus y, I guess. If we're doing it that way, right? That's how far it has to. Well, no, that's not. I'm sorry. I keep wanting to say it the way I like to think of it. You can think of it. Okay, it's going to travel dy, and then that small dy is going to travel. The amount of weight that's being moved is this distance, 1,000 minus y, times 9.8, times the density of that part of the cable. So basically, you can think of a bunch of mass moving a small distance, or a small mass moving a bunch of distance. Those are kind of the two ways you can do it. Actually, now that I said it that way, it makes sense. Let me say it again. You can either think of it as a small, I should say force really, not mass, moving a long distance, and then thinking about all the different small masses, each moving along a different distance. Or you can think about it as a large mass moving a small distance. So at the beginning, this giant mass moves a tiny bit. And then next, there's a little bit less mass, like some of it's already on the boat, that moves a tiny bit. And then there's a little bit less, and it moves a tiny bit, but you're still moving, each time you're moving up a little bit, you're moving a bunch of stuff. Yeah, that's what I thought you were thinking of, Maureen. And you're probably not wrong about how you wanted to conceptualize it. It just wasn't working in my brain. So anything else to say here about this? I don't think so. Yeah, okay, so so let me ask you guys, has anyone been asked to do a leaky bucket problem? Yes, okay. Then I guess we'll do a leaky bucket problem, even though they're everyone's least favorite. And then we'll move on to the thing I have on the other board. So we'll do one more of these where you're essentially just lifting stuff. And then we'll move on. Now the leaky bucket problem definitely is a problem where you do have to kind of think of things in both ways. You have to be able to think of things as a small mass that's moving a large distance, or small force that's moving a large distance, or a large force that's moving a small distance, right? Basically all the force moves a tiny bit, or some small force moves all of it. All right, do I have a leaky bucket problem? Yes, I do. Cool. A leaky bucket weighing 5 pounds is pulled up by 20 feet by a uniform rope weighing 0.2 pounds per foot. Okay, so I'm not gonna write all the things, I'm gonna say the things. So we've got a bucket. And that bucket on its own weighs 5 pounds, right? We're not counting the water yet that's in there. So the bucket itself weighs 5 pounds, and it's pulled up 20 feet. So it's going to go 20 feet. I guess I could draw this, not dashed. It's going to go 20 feet by a uniform rope weighing 0.2 pounds per foot. So the rope weighs 0.25 pounds per foot. Or I could have just said there's 20 feet of rope and it weighs 5 pounds, and then I could have said figure out the weight density. Oh, it's 5 pounds per 20 feet. It's 0.25 pounds per 1 foot. And then finally, the bucket is initially full of water weighing 16 pounds. So down here, the water in the bucket, so right, all the water in the bucket, that water weighs 16 pounds. Now, as we lift the bucket up, the weight of the bucket is going to stay the same, but the weight of the water is going to change because we're losing water. So the rest of the problem says, I always hate these problems where like the bucket's empty at the top, because you're like, well, that's dumb. Why are you lifting this bucket up to the top if you're not getting any water? But this problem is set up that way. So the bucket finishes draining just as it reaches the top, which means like, oh, why would I even do this? That seems like a waste of work. So at the top, we're going to have a bucket, still weighs 5 pounds. In fact, it only weighs 5 pounds because we have 0 pounds of water. Okay, and so we want to figure out how much work was done in lifting the whole setup. That means the bucket, the rope, and hardest of all, the water in the bucket. So the bucket itself was easy. The work done for the bucket, and again, right, this is 20 feet. The work done for the bucket is just going to be the weight of the bucket, which doesn't change, times the constant distance it travels. So it's going to be 5 pounds times 20 feet, which is going to be 100 foot-pounds. Great. The work for the rope, which again is something we've talked about a couple times already. Gosh, how do I like to think of this? So again, yeah, I'm going to do it the way I'm used to doing it just because that's the way I'm used to doing it. So I'm thinking of, right, this small segment has moved up y, where the bottom is y equals 0, and the top is y equals 20. And so I'm going to say in my brain that the work done moving the rope, well, this small segment of rope, which weighs 0.25 pounds per foot times how long it is, which is dy feet. That's the force or the weight. So 0.25 dy times the distance. And the distance that has to travel is 20 minus y. Or you could alternatively say, once the bucket has gotten up to this spot, how much work does it take to move it up just a little bit? Well, the distance it's going to move is going to be the dy, and the work that's going to be done when we move it, that small dy, is going to be how much this whole piece of rope weighs. Well, that rope is 20 minus y feet long, and it weighs 0.25 pounds per foot. Same thing either way. It's just a different way of imagining, right? This way I'm thinking of this is the force and this is the distance. This way I'm thinking of this is the force and this is the distance. But I'm still multiplying the same numbers together, right? Still the same. So in either way you want to think of it, we're going to end up integrating from 0 to 20 of 1/4 20 minus y dy. It's going to work out just like all the other ones did, where you're going to get 20y minus y squared over 2, from 0 to 20. Don't forget the 1/4. When you plug in 20, you're going to get 20 squared minus 20 squared over 2. 20 squared is 400. 20 squared over 2 is 200. 400 minus 200 is 200. So you 200 times 1/4, which is 50 foot-pounds. So far, we've done 100 foot-pounds for the bucket, 50 foot-pounds for the other thing, the rope. And now we're going to talk about the water. So the water, I really do have to kind of think about in this second way, where the water is going to move a small distance and there's going to be some amount of work done by moving that force. Because the problem is, for the water in the bucket, the amount of water, the weight of the water is changing. So when we think about it moving, from here up to here, if it's a small distance, we can kind of make the assumption, like we do whenever we're integrating stuff, that from there to there, it's essentially a constant amount of force, right? Like the weight of the water in the bucket isn't changing much. So we can say, okay, for the water, when it moves from there to there, it's going to travel a distance of dy. So I should do the work for the water. So I always write the distance second. I don't know why. It just is what I do. So the distance is going to be dy. And the force is going to be how much the water in the bucket weighs when it's that high, which we have to figure out, which I'm never good at doing in a consistent way. I'm always going to think of it as being some sort of linear function. So I know that when the height is 0, the amount of water is 16. So when y equals 0, water is 16 pounds. And when y equals 20, water is 0 pounds. So every foot I go up, I lose some amount of pounds. And really, I'm just thinking, this was like, I'm just trying to write a linear function. I'm trying to write water in terms of y. So I'm going to say, okay, I know that the slope, so water is the dependent variable, its change goes on top. It's 16 minus 0 over 0 minus 20 pounds per foot. 16 over negative 20 is negative 8/10, which is negative 4/5. So then I know that when I plug in 0 for y, I should get 16 for water. So the water weight is going to be negative 4/5 y plus 20. I bet there are easier ways to get there. For some reason, my brain has just never gotten around this particular, an easier way of doing this, but we can check. If y is 0 at the bottom, This is definitely a reason why it's better to do it, I think, with y0 at the bottom for this type of problem. If y0 at the bottom, the weight of the water is 0 plus 20. Well, that's not right. It's supposed to be 16. You guys are like, what's he doing with that 20? Oh, yeah, it's supposed to be 16. Okay, now it should work. If y is 0 at the bottom, the weight of the water is 16. If y is 20 at the top, negative 4/5 times 20 is negative 16, plus 16 is 0. So that seems reasonable to me. That is definitely correct. So that's going to be the weight of my water. It's going to be negative 4/5 y plus 16 pounds. Okay. And then I'm going to have to erase something. I guess I can erase all this here. So the work for the rope was 50 foot-pounds. And then the work for the water should have been in blue. That would make more sense. We're going to do the integral again from 0 to 20 of the weight of the water in the bucket times it moving a small distance. So negative 4/5 y plus 16 dy. And then we're going to integrate. So we're going to get negative 4/5 times y squared over 2 plus 16y from 0 to 20. Which is going to end up being, let's see here. So I'm going to plug in 20. I get negative 4/5 times 20 squared is 400 over 2. Plus 16 times 20 is 320. Minus 0 plus 0. I haven't been saying that every time, but in all these examples, when we plugged in 0, when we would have plugged in 0, we would have gotten 0 back. So let's see. 4 over 2 gives me a 2 there. So I get negative 800 over 5, which is negative 160, plus 320, which is positive 160. So the work for the water is 160 foot-pounds. And then the total work done looks like it's 310 foot-pounds of work. 100 plus 50 plus 160. What about the bucket? The bucket was the 100 foot-pounds. Right, the work for the bucket was the 5 pounds that the bucket weighed times the distance the bucket traveled, which was the 20 feet. Yeah. So again, so definitely for these leaky bucket ones where the weight of your thing is changing as you go up or go whichever way, you definitely have to imagine it as, oh, I've got some force that's moving some small distance, which is also the way some of you were imagining the work for the rope, right? Work for the rope, you've got some force, the length of the rope times its density times some small distance. Could you quickly redo the work for the rope? Sure. I'll write it out here. So the work for the rope, and again, the way, so I'll even say it the other way. So the work for the rope, again, I'm thinking of the bucket at this height. And so the work for the rope is, so I'm thinking I pulled the rope up to this height. So I don't have this down here anymore, right? That's gone. I'm saying, okay, how much work does it take to move the rope just this small little distance here? Well, the work for the rope there is going to be the small distance it travels, which is dy, times the weight of the rope, which is the length of the rope, times its weight density. So that's going to be 20 minus y times its density, which is 0.25, I believe. So that's the work to move the rope just a small distance. And then to find the total work, you're going to integrate from all the small distances. So it starts as low as 0, goes up to 20. So the work for the rope is the integral from 0 to 20 of 20 minus y times 0.25 times dy. You probably could do the water and the bucket in one integral. I usually like to kind of separate that out because it's just, I mean, you're right. It's not really harder to do the water with the bucket. You would just add 5 to this equation. So right, you would say, oh, the weight of the water plus the weight of the bucket is just -4/5 y plus 16 plus 5, or -4/5 plus 21. That's also fine. Usually people do it separately just because it's easier to mentally conceive of what's happening if we break it all up into the pieces. Yeah, so we add up all our totals, and 100 plus 50 plus 160 is 310 foot-pounds. So yeah, leaky buckets are always fun. All right, let's move on and talk about work done pumping some volumes like this next one, which is why I wasn't using the other side of the board, because I already had this question written. I was like, I don't want to erase it. So find the work required to pump water, which has a weight density of 62.5 pounds per cubic foot, out of a 6-foot radius hemisphere bowl filled to a depth of 3 feet. So let me just grab one thing here. Sure. All right, so let's draw a picture. So here's our bowl. It's a hemisphere. It's got a radius of 6 feet. And it is filled to a depth of 3 feet, which I guess I can use blue. We want to know how much work it would take to pump all of this water out the top. That's all I want. Okay. And again, you really can do this a lot of different ways. Oh yeah, you really can do this a lot of different ways. So yeah. So first of all, typically, well, no, I'm going to think about what's going here. So when we're trying to move water out, again, work is force times distance. So we're trying to kind of grab a slice of the water that's all going to move the same amount of distance. In this case, it's some horizontal slice, because some horizontal slice is all going to have the same vertical amount of distance to travel. So I'm trying to grab a slice kind of like that. And so I want to know, what's the work to move that slice? Well, it's going to be the force times the distance. Force is just volume times density times the distance. The volume is just the area times the thickness. So that's going to be pi times whatever the radius of this disk is squared times the thickness, which is dy, times the density times the distance. So that's the idea for this particular idea, right? The volume of this is pi r squared times thickness. The density is given as 62.5 pounds per cubic foot. And the distance is something we're going to have to figure out. Now, here's what I'll say. This is a 3D shape, or I've drawn it like a 3D shape. I don't really need the 3D-ness after I've determined like what the volume equation is. So what I'd really rather do is draw it more as a 2D shape, like that. Where I really want to know, and I guess I should draw my strip too. All right, so here is my slice. And here's the top of the water. I want to know how to find the volume of that. Because again, right, if we think about this, the slice being higher or lower, it's going to have different volume if it's lower and higher, because it's going to have less width or more width, depending on how we go. And so, yeah, there are so many different ways you can set this up. I would probably set it up. So typically you like the center of your circle. I like the center of my circle or my hemisphere. I typically would like that to be on my axis, meaning I'm thinking of this kind of as the X and the Y axis. I would really like for that to be Y equals 0. And now I'm kind of sold on the idea of, if we go up, it's positive. If we go down, it's negative. So I'm kind of thinking of the bottom of this as y equals -6. And then I know that this here the top of the water is at a height of 3, so that's going to be y equals -3. And then this is going to be kind of interesting, right? So this is where things might start to fall apart for me. What's that? I guess it's y. What's that? I guess it's -6 minus y. This is, I mean, like I'm trying to justify doing this a different way, but this way I feel like really does work. Maybe I'm gonna mess it up and it's gonna be terrible. I don't think so though. Some other people do just say this is y equals 0, this is y equals +6, and then this is still y, and this is, it's fine either way. So here's what I want. I want the volume of that. So I need the volume of this disk. I need this radius here. That's my radius. Well, I know that this radius of the hemisphere is 6. And I know that this length here is y. So I can find that radius using the Pythagorean theorem by saying that r squared plus y squared equals 6 squared. So that r squared equals 36 minus y squared. And I could solve for r, but I don't need to because my equation has r squared in it. Okay, so now I'm going to say that the work of my slide, or the work of my slides is going to be, so it's going to be pi times r squared. So it's going to be, let me write that here. It's going to be pi times my r squared, which is 36 minus y squared, times my dy, times my density, which is 62.5, divided, I'm just going to say 62.5, times my distance, and the distance this has to travel is y. We could make the bottom of the bowl 0. The only reason I was trying not to do that, although I probably would have done that normally, is because it makes this equation a little bit less nice. But you're right. I probably actually would make the bottom of the bowl 0. I could, so yeah, I feel like as much as I kind of like this, I really don't. So let me use a different color to show you just whatever. So instead, if we make the bottom of the bowl 0 and the top of the bowl 6, then that's y, and that's 6 minus y. And so then, if you're trying to find r here, you've instead got r squared plus, instead of y squared, you've got 6 minus y squared, which isn't terrible, it's just different. So you got r squared plus 6 minus y squared equals 6 squared. And then solving for r squared, you get r squared equals 36 minus this. And this, if you square it out, is 36 minus 12y plus y squared. So you can say that in this case, r squared is 12y minus y squared. It'll also work. I'll probably end up doing it both ways. So you can do it this way, or I'm going to erase this. Sure. Or we can say the work of our slice in this other frame of reference is pi times r squared, which is 12y minus y squared, times our 62.5 times dy times 62.5 times, now instead of y, it's 6 minus y. Okay. I feel like I need to, let's just use the other side of the board. So I can come back and look at this and make sure we didn't screw something up. So, in red, we're doing this one from -6 up to 0. So the work we could either calculate is the integral from -6 to 0 of pi times 36 minus y squared times dy times 62.5 times y. I'm going to factor out the 62.5 in the pi. I didn't leave myself room for. And then we have what? 36 minus y squared times y times dy. Or in blue, still have the 62.5 and the pi. Integral from 0 to 6, right? Because we're starting at 0, we're ending at 6. That's a 6. And then it's going to be 12y minus y squared times 6 minus y dy. And while I certainly personally feel like this feels better because it just seems more sensible, this is probably easier to compute. So that's probably why someone might want to do it this way instead of this way. And I'm really hoping these turn out to be the same. I have a worrisome feeling that they're not going to be the same. Let's do this first one real quick since it's easy. 62.5 integral from negative 6 to 0 of 36y minus y cubed. And then if we integrate that, we get 36y squared over 2, which is 18y squared. Although I actually think I want to leave it as 36y squared over 2. You'll see why in a second. Minus y to the 4th over 4 from negative 6 to 0. We plug in 0, we get 0. Minus, we plug in negative 6, and we get, and I'm worried, we get 36 times negative 6 squared, which is 6 times 6 times 6 times 6. I'm going to write that as 6 to the 4th. Minus negative 6 to the 4th over 4 is, again, 6 to the 4th. Yep, and I'm off by a sign, which I was worried about. Yeah, we're definitely off by a sign. That's frustrating, but not impossible to fix. So here we're getting 6 to the 4th times 1 minus 1/4. So it's negative, which is going to be 6 to the 4th over 4. That's going to be something, I don't know. Sure. Why is it negative? So this is where I was worried that I was making an error. And I don't know if I have a good way of explaining it. Is this really y or is this negative y? Maybe that's what the issue is. So I will say, I was trying to do it this way because I thought it might be nicer. But my brain just doesn't want to do it that way. Let's do it this way. Oh, and sorry, and I forgot the 62.5 pi. Right, that should be times 62.5 pi. Let's do it this way because it's probably nicer, or at least easier to comprehend. So we multiply this out. I get a positive y cubed. I get a minus 6y squared minus 12y squared, which is minus 18y squared. And I get a 12y times 6, which is plus 72y. And then we integrate that. What is the symbol that is multiplying with volume on the other side? It's a delta. It's a lowercase delta, like in a delta epsilon proof, and that is usually the symbol used for density. Specifically for weight density, meaning a weight divided by a thing, as opposed to regular density, which is a mass divided by a thing, which usually use rho for regular density. So here we've got, I'm going to integrate, I'm going to get y to the 4th over 4 minus 18y cubed over 3, which is just 6y cubed, plus 72y squared over 2, which is 36y squared. From 0 to 6, and then we pray that it turns out to at least be the same, even if it's not the right sign up there. So we get 62.5 pi times 6 to the 4th over 4 minus 6 to the 4th plus 6 to the 4th. Do you guys see that? Let me say it again. 6 to the 4th over 4 minus 6 times 6 cubed is 6 to the 4th, plus 36 times 6 squared is 6 to the 4th. So those will cancel out. So we still get the same answer, except that we were off by minus 7 before. So as you might notice, 62.5 times 6 to the 4th over 4. This integral was a little more, not a lot more complicated, right? I mean, this wasn't so bad to multiply out. Yeah. Oh, mother. Darn. I made a mistake. You guys let me get away with it. I blame you guys, because, yeah. So here's the mistake I made. Which is not terrible, but it's a little terrible. We integrated from 0 to 6. But the bowl is only half full. We should have actually integrated, if we're doing it the blue way, from 0 to 3. At this point, I really would prefer not. I mean, so I guess, that is not hard to fix. Right, that's actually pretty easy to fix. So it should actually be 3 to the 4th, which is 81 over 4, minus 6 times 3 cubed, which is 6 times 27 is 162, plus 36 times 3 squared, 36 times 9 is 360 minus 36, 324. Okay, so it's that. So that brings up an important point though, right? It's really important that you think about your physical thing, like, oh yeah, I'm only trying to find the work it takes to pump out the stuff that I have, where the stuff starts here and ends here, right? The stuff doesn't go all the way to the top of the bowl. So that's actually a good lesson to learn in this example. Let's look at some more. So I should just, as much as I would like to try and show you guys alternative ways of thinking these, I know how my brain gets it. And that's the way I should be trying to explain it, because that's what my brain does. So let's see, we have a cylindrical tank, half full of water. Like this. It's half full of water. The cylindrical tank is 10 meters tall. And it has a radius of 2 meters. And so the question is, how much work does it take to pump all the water out the top? It's work to pump the water out the top. For the metric system, we have a different density. So the density of water here is, I think we usually use a rho for an actual density as opposed to a weight density. It's 1,000 kilograms per cubic meter, right? This is a mass density, mass per volume, whereas the previous one was a weight density. It was weight per volume. And of course, gravity, 9.8 meters per second squared. So how much work? Well, again, the idea is still the same. We want to think about how much work it takes to move a slice of water. So this slice of water. Okay. So the work for my slice is the force or weight of my slice times the distance it's going to travel. And I'm going to set this up as, again, I'm going to think of the bottom here as y equals 0, the top here as y equals 10. This is going to be at a height of y, and it's going to travel a distance of 10 minus y. And I will just say, so I'm looking at these notes that are Grant's notes, which are great. Grant has some really nice pictures here. I encourage you to look at them. In fact, I'll even throw them into the chat here. But what I'll say is Grant definitely does it where he starts with the top being, oops, sorry. I said that privately to someone, send it to everybody. Let me send it to everybody. Grant definitely sets them up where the top is like y equals 0 and the bottom is y equals 0. Oh, actually, he set it up both ways in this one, which is kind of smart. So the nice thing about doing it the other way is that usually you're not multiplying by 10 minus y, you're just multiplying by y, which makes it a tiny bit easier. Oh, well. I like to do it the hard way, I guess. So the force, aka the weight of this slice of water, is just the volume times the density. And the distance, we already know that this slice is going to travel 10 minus y meters. Okay, the volume of that slice is pi r squared times the thickness. And here, unlike the previous problem, the radius isn't changing. Right? The radius for any slice is going to be 2 meters. So here the volume is going to be pi times 2 squared times dy. That's the volume times the density, which is 1,000 kilograms per cubic meter. That's the mass of that slice, right? It's volume in cubic meters times kilograms per cubic meters. And then we have to multiply by gravity so that we actually get a weight, not a mass, times 10 minus 1. Oh boy. So the work total is going to be the integral from, how low is our integral going to start at? How high are we going to integrate to? It's not 10, it's 5 because it's half full. And then it's going to be this terrible mess. And the only thing that we're really, right, the only thing that's really going to integrate is 10 minus y. Everything else is on the outside. So I've got 4 times pi times 1,000 times 9.8, which is, I don't know, 4 times 1,000, 4,000 times 9.8. That's 39,200 pi out in front. Times the integral from 0 to 5 of 10 minus y. That's not so bad. I'm not going to finish that because I think you guys can finish that. Okay. So, I don't want to do that. All right, let's see. Oh, fluid force. Yeah, we should use the last. So we can do more of those next time, I guess, but we should also talk about fluid force due to pressure. So the idea of fluid force due to pressure is that basically, if you've got some object underwater, the weight of water on top of it is literally all the water that's above it. So, yeah. For example, if I have a fish tank like this, I've got this fish tank, and let's say the fish tank is kind of big. It's 7 feet long. It's 2 feet deep. It's 4 feet high. Any little section at the bottom of the fish tank, there is 4 feet of water that is literally on top of that point. And so the fluid force is equal to the amount of water that is on top of your area. So if you've got some small little area here, then the fluid force due to water is the weight, right? Because force is just a fancy name for weight. It's the weight of all of the water in this little column that is sitting on top of that plate. And that's not too terrible to calculate. It's just the volume of the water times the density of the water. So the fluid force is just equal to the volume times the density. Where if it's in the US system, right, it's going, well, in either system, the volume is just going to be the depth, right, how deep it is, 4 feet in this case, times the area. And the density of water is either 62.5 pounds per cubic foot, or it's 1,000 kilograms per cubic meter times 9.8 meters per second squared. So it's really easy to calculate fluid force if you're being asked to find the fluid force on something that's all at a certain depth. For example, if I wanted to find out, what's the fluid force on the entire floor of the aquarium? Well, the fluid force on the floor is super duper easy. I'm really just saying, how much does all that water weigh times how deep is, oh, no, I'm really just saying how much does all that water weigh? Right? Because it's the area, which is 2 times 7, so 14 square feet, times the depth, and this whole thing is at a depth of 4 feet, times the 62.5 pounds per cubic foot. So if you multiply this out, you get some number. It's, I don't know. It's something. It's, I don't know, calculator time. 14 times 4 times 62.5. 3,500. So it's 3,500 pounds. That's it. 3,500 pounds of force are on that floor of our aquarium. Okay, but here's a different, more interesting question. How much force is on, let's say I want to say the long side. So how much force is on that side back there? Well, the problem is not all that side is at the same depth. So the bottom part has a lot more force on it than the top part. So of course, when it's variable like this, we're going to have to iterate. So what we're going to do, erase this picture. We're just going to think about, okay, so just like before, we were talking about the slices that had to travel different distances. Now we're going to think about slices that are at different depths. So this strip here, and again, I am a sucker for doing it the way I always do it. The bottom is y equals 0, the top is y equals 4. This strip here is at the depth of 4 minus y, because this is the height of y. And that strip has an area that is just its length times its height. So the force on this strip is going to be, okay, I just said it's the area times the depth times the density, which is just that delta symbol. So the area is 7 times dy times the depth, which we just said was 4 minus y, times the density, which is 62.5. And that's the force that's on that strip at that height y. But then I'm going to let the heights be as low as 0 and as high as 4. So the total force is going to be the integral from 0 to 4 of 7 dy times 4 minus y times 62.5, which I would probably write as, I'd probably write the 7 and the 62.5 out in front. So it's 7 times 62.5. I don't know, I circled that. Times the integral from 0 to 4 of 4 minus y dy. That's the idea there. And it doesn't, I know sometimes you're like, well, isn't it on the side? Like, it doesn't matter. It doesn't matter if it's on the side or if it's flat or if it's whatever. It just matters how deep it is and how much area there is for the fluid to act on. Okay. I mean, I guess we could finish this problem. That would end up being 7 times 62.5 times the integral of this, which is not unlike other things we've seen, 4y minus y squared over 2 from 0 to 4. You're going to get 16 minus half of 16, so you're going to get 7 times 62.5 times 8. Something I've noticed over the years is that 62.5 times 8 is 500. 62.5 times 2 is 125. Times 2 is 250. Times 2 is 500. Times another 2 would be 1,000. So 62.5 times 16 is 1,000. That actually comes up somewhat frequently, so it's something to be aware of. So that's 500 times 7, which is also 3,500, which is totally coincidental. Right? It's always like, oh no, that's a terrible coincidence. Like I didn't mean for that time. But yeah, it is actually just a coincidence. It is not, should not necessarily be the same. Okay. Yeah, let's do, we might have, yeah, we have time to finish this one. Okay, circular window with a radius of 1 foot is submerged 100 feet below the water. How much force is on it? Okay, so here's the picture I'm thinking of. Got my water, and I've got my circular window, and it's submerged 100 feet below the water. So I'm thinking of this being 100 feet. And I think it's going to be easy. No, I'm like, I want to do it one way, but I really just don't. So I'm just going to do what I used to do. I'm going to call this y equals 0. I'm going to call this y equals 100. And I'm going to live with the consequences. My radius is 1. So that's y equals 1. That's y equals 2. And I need to figure out how much force is acting on a strip, a horizontal strip, because the horizontal strip is all the same depth. So I'm going to draw a strip right there. And I need to find how much area that strip has. Because the force is just going to be the area times the depth times the density. All right. I might have wanted to make a different choice here. We'll see in a second. So I'm saying that this is at a height of y. And I want to find, I'm going to draw a bigger picture. Right? I want to find the length of this. Well, I can draw this, which has a length of 1. The radius of the circle is 1. And I know that if this is y, then this segment here is y minus 1. And this length here is, I'm going to call this something, I don't know, let's call it x. And that's half, right? So y minus 1 squared plus x squared equals 1 squared. X squared equals 1 minus y minus 1 squared. So x equals the square root of 1 minus y minus 1 squared, which ends up being minus y squared plus 2y, and then the 1's cancel. Oh yeah, there's definitely a reason we don't want to do this. So here's the problem with this setup here. So this is terrible. We're going to fix it. The problem is that the area of this strip is 2x times dy. So the area of my strip is 2x, right? That's x. There's another x times dy, which is 2 times that dy. And I will tell you, that's really hard to integrate. like probably trig substitution integration, which we don't have yet. So this is a prime example of why you often want your center to be at y equals 0. So instead of making this y equals 0, y equals 1, I'm going to make this y equals 0, this y equals 1, this y equals -1, and this y equals 99. So that now, instead of this whole distance being y, it's really just from y equals 0 to there being y. Which means, instead of this being y minus 1, this is now just y. This isn't y anymore. And now this isn't y minus 1, it's just y being squared. So look what happens. And you know what? I think it's still trig substitution. You get y squared plus x squared equals 1 squared. You get x squared equal to 1 minus y squared. And x is the square root of 1 minus y squared. Okay, I still think we're kind of in a world of, oh no, we're not. We're maybe okay. Yeah, we're gonna be all right. So check this out. Area is gonna equal, so sorry, the force is gonna equal the area, which is now 2 times the square root of 1 minus y squared, times the depth, which is 99 minus 1, times the density, which is 62.5. Okay, there's something really cool to be seen here in these last 2 minutes. And we're going to integrate this from where to where? From how low does my circle go to how high does my circle go? In green. Yes. All right, I have to either erase or let's just go to the other side. So I'm going to integrate this from -1 to 1 and watch how cool it's going to be. You guys are going to be like, wow, that's amazing, James. This is one of those problems that comes out to be that really, like, if you know your stuff, it's like, oh, this is super cool. So we're doing the integral from -1 to 1 of the square root of 1 minus y squared times 99 minus y times 2 times 62.5 and bring out front is 125. All right, I think that's it. Right, I've got my area, which is 2 times x. I've got my depth, which is that. I've got my density, which is that. Okay. Watch this. I'm going to break this up into 2 integrals. It's going to be the integral from -1 to 1 of 99 times the square root of 1 minus y squared, plus the integral from -1 to 1. I should say minus, really, not plus. The square root, y times the square root of 1 minus y squared. Now check out this trickery. The integral, 0. How do we know it's 0? Because y times the square root of 1 minus y squared is an odd function. Yeah, and we're going from -1 to 1. So its integral is 0. You can also do a u sub here. If you did the u sub, u equal to 1 minus y squared, and your du is whatever, it works. If you change your limits of integration to u limits of integration, you get 1 minus 1 and 1 minus 1. So you're integrating from 0 to 0, which is automatically going to be 0. Kind of cool. This one, we might not know how to integrate this yet, but I don't need to because that's just the equation of the top half of a circle, or the right half of the circle if you want. So, right, this is 125 times 99 times integral from -1 to 1 of the square root of 1 minus y squared is the right half of a circle with a radius of 1. So the area is 1/2 pi times 1 squared. And this kind of thing happens more often than you might imagine. So kind of neat.